Consider a system composed of 20 particles distributed among 4 bins. Consider the following 5 distributions of 20 particles among these bins. So here you see the 5 distributions and the 4 bins with the number of particles in each bin. A binomial coefficient expression is useful because it gives us the number of microstates for a number of particles n distributed according to a particular arrangement. So for part A, calculate the microstates given this set of arrangements. So what you do is you take the binomial coefficient expression to find the number of microstates. So the number of particles we have is 20. And you have 20 particles in the first bin, factorial, 0 in the other 3. And this would give you an answer of 1. So there's only 1 microstate. For part B, you have these different set of arrangements, and what you do is use the same equation, the binomial coefficient equation. And so the number of microstates would be equal to n, which is 20. It does not change because you have 20 particles. Then you arrange in the first bin 18 particles in the first one, 1 in the second, 1 in the third, and 0 for the last one. And that should give you 380. For the next problem, similarly, you use the binomial coefficient expression. So the number of microstates would be equal to 20 factorial over 14 factorial, 3, 2, and 1 factorial, and that should give you 2.33 times 10 to the 6. That's the number of microstates available. For this question, the next one, it's very interesting because you have to calculate the molar entropy involved in going from distribution 1 to 5. So you're trying to solve for the change in entropy from going from 1 to 5. So to do that is you're going to look at distribution 1, which is 20, 0, 0, and 0. And then for the second one, that is the fifth, 8, 6, 4, 2. So the equation you need to solve this is the Boltzmann entropy equation, and this is written as S equals Kb, which is Boltzmann constant, natural log of the number of microstates. So S of 1 would be equal to Kb, which is Boltzmann constant. Kb is equal to 1.38 times 10 to the negative 23 joules per Kelvin. Kb, natural log of the microstates. So for the first distribution, we calculated the number of microstates to be 1. So I'm going to put natural log of 1. Then to solve this equation, it would give you overall 0, because natural log of 1 is 0. And to solve for this fifth distribution, Kb, natural log omega. So for the fifth distribution, we did not calculate that, but we can calculate that right now. So W is equal to 20 over 8 factorial, 6 factorial, 4, and 2 factorial. And this should give you around, which should equal around 1.75 times 10 to the 9. So if you plug that into here, you should get an entropy at the fifth distribution level to be around 2.93 times 10 to the minus 22 joules per Kelvin. So to find the change in entropy, you just subtract S5 and S1, and that should give you 2.93 times 10 to the minus 22, since the first one is 0 joules per Kelvin. And to get joules per mole per Kelvin, you should multiply by Avogadro's number, so 6.022 times 10 to the 23rd particles per mole. And you should end up with around 177 joules per mole Kelvin.